Okay, thank you for coming. My name is George Christandakopoulos. I'm going to be talking about the concurrency and coordination runtime and the Decentralized Software Services Toolkit. And we could have added more words to that title, like my last name. But this will do. I've been with Microsoft for 12 years. I started in Windows NT. I was there for 4 years in the base group. I then went to Xbox. I was part of the small team that did the system software for the first Xbox. And then I joined an incubation that we were trying to create a new programming model, a new application model for software in general. So after that, we actually used robotics as a way to bring that to market, get some real feedback, make it a real product. And here we are today making it back into a general framework because of customer demand. So we're announcing the CCR and DSS toolkit. This enables developers to easily create loosely coupled, concurrent, and distributed applications. It allows early adopters to use these technologies today to build commercial and non-commercial applications. And basically, you get access to technology that one day will be integrated in .NET, and you will expect some churn when that happens. But this same programming model, we're working with the developer division to bring in the main framework. So our approach was find at least one market that has a need, and really you don't need to persuade anyone, for concurrency and distribution. And robotics was that market. A lot of people came to us and said, we want to focus on building complex robotic applications, not building the software infrastructure for the robot. So they're complex machines. They heavily depend on coordination between software components. The actual application, like a robot autonomously navigating from one room to another room, as an example, is a composition of hardware and software. And it's literally loosely coupled in many ways. It's built by different people at different times. It's running across multiple heterogeneous processors. And you really care about performance and determinism in a physical sense. Like your robot is going 2 meters per second, a hiccup could run it through the wall. So you have a very concrete way of measuring that your software doesn't work. The other one is that we wanted to enable reuse. There's a lot of smart people in robotics, but they really built up everything from scratch almost every time, and they don't share that easily. And progress comes from that type of reuse. So really briefly, what is the CCR DSS toolkit? Essentially, it has 3 pieces. The most important one is the first one. It's the runtime. We're a few managed libraries. We're pure managed .NET code. And those libraries are essentially the coordination and concurrency runtime. This is a very small managed library that is our programming model and our concurrency engine. And then we have the distribution engine on top, the distributed system services, that basically lets you talk across machines, gives you deep isolation, and we call that DSS. In the toolkit, you will also find authoring tools that we developed to make building distributed applications easier. It elevates our model, our concurrency model, at a visual level. You can do fast prototyping, and also you can compile down to human-readable C#. The other thing that comes with it is we have a lot of tutorials, we have video tutorials, and we also have infrastructure services, like services that create instances across machines, or let you find services, or do logging and stuff like that. And that's all part of the toolkit. So what happened is we go out with this platform for robotics. We knew it's more general than that. But it's always nice to have customers come to you and say, we really want this, but my manager won't buy it because it has the name robotics on it. So even so, just based on Channel 9 videos, I'm only going to talk about a couple of these instances. We have companies like Tyco. They're like a $41 billion software and hardware business. And Siemens that now have applied this. And they're processing hundreds of millions of operations per second, per hour, per day. And the other thing is, internally at Microsoft, the homepage now at Live does all its I/O coordination in the context of ASP using CCR. So we're talking, again, literally in the billions of operations using this engine right now. So I'm going to talk about the CCR first and give you a little introduction. And then I'm going to talk about the customers, how they use it. And then I'm going to do a deep dive. So once you know how customers are using it, you'll get an idea how this is positioned versus other things that Microsoft is doing at the same time. So why CCR? So concurrency is good, because you can process a lot of things. So we give you the ability, you don't have to rewrite your code. As you add cores, we will just use them. That, of course, gives you scalability. It gives you responsiveness. And because of our affinity towards asynchronous processing, you can now exploit latency. So you're not afraid anymore to do a lot of asynchronous operations. You can exploit that while you're waiting, but without blocking OS resources. The second thing is coordination. I always believed, actually, that the trick is not concurrency. It's not parallelism. That just happens naturally. The trick is coordination, because you're really scared of doing many things at the same time because you can't deal with failure. You can't keep the program logic in your head. So we give you these concise primitives to basically very easily describe your intent, and then we'll take care of expressing your program in the execution engine. So the other thing we did is we really wanted to focus about failure. When you have concurrency, failure becomes very complicated in this complex execution graphs where it can happen at once in multiple spots. So clearly try catch won't work. So we have extensions of that work across cores and they work across machines. And the runtime aspect is we actually did a lot of thinking. We didn't just give you another scheduler. We gave you a scheduler that is composable, it is fair, it's very responsive, and we do rate throttling. We can eliminate thousands of lines of code with a single policy that says if you have more than 5 tasks per second, either throw them away or block the sender. So having this time domain aspect to concurrency is extremely important, and it's something that, again, we would like to see in the main frameworks. So I'm going to talk about Siemens right now and how they used it. I have some data sheets that describe the case studies in much more detail. So you can come here later and pick up, or you can go to our booth. So this particular group of Siemens handles about 70% of physical mail in the world. They have these massive conveyor systems, AI agents, a dual CR, and they have this software construct called a Blackboard. It's basically a publication subscription system, and you have multiple beliefs, and they're message-based, and they basically argue about where this piece of mail that's flying at 10 meters per second through this conveyor belt, where does it need to go? And it does multiple database lookups and all that. So they built their new version, and this is millions of lines of legacy code. They built their new version, the core of the new version, on the CCR. They're processing 500,000 operations per second right now. This is all in process, so they still have networking to go, but in process, it's 500 operations per second. And the version is scalable, readable, and extensible according to them. These are some of the quotes. They actually evaluated other managed runtimes, Java, and they saw that our peak throughput is literally, we can get things within 400 nanoseconds, which is as low as you can task switch in NT. The other thing is we have very low jitter, and we have some custom timer logic for periodic tasks. And the other thing is, while we have a very different programming model, which is why you can also use other technologies, this different programming model, in some ways, a lot of people get this unification, having this small set of primitives to express a lot of patterns. So again and again, they're telling us, they come back from a conference of the Channel 9 video, within 2 days, they have this thing running. It does depend on your background, though. I think there's a class of people that get it right away, and some maybe that need to see it in action a lot more. The other example is Tyco. So they do event management systems. They do security systems. They basically gather a lot of events that happen from cameras, from doors opening and closing. They give you management on all that. And again, they move to CCR as the glue. So CCR can be used on top of WCF, for example. So instead of the APM pattern, they use CCR and WCF. And they basically coordinate a lot of operations per second across many machines. And again, they dropped this in. We didn't know, by the way, both Siemens and Tyco, we didn't know they had done this. They just watched the video, and the next thing I know, it's like in front of a $9 billion business, which is kind of a nice, refreshing thing for the customer to come to you. So that's why we're excited and we're here. So the other thing they noticed is that it was very robust. We really isolate failure. These random exceptions won't bring your node down, your process down, and can have a concise way of describing where to deal with failure. So this is some other thing. They must be at the sweet spot of the CCR because they see linear scaling. They really do. The other thing is, again, he came back from a conference. Within 2 days, he had this thing running with the CCR and his legacy code. So let's go a little bit more now. I'm going to do a deeper dive, and I'm going to show some code. And then I'm going to show some simple demonstrations on the CCR. So we're about message passing. But unlike a lot of message passing you've seen in the past where you go into spaghetti very soon because of delegates and all that. We really did a lot of thinking to avoid that. Now, the beauty about this particular paradigm is that you don't have to deal about threads, locks, semaphores, or anything else. It's kind of a unifying way to deal with signaling, resource contention, and messaging. We're essentially a data dependency scheduler. If you have something you need to compute something further, you just describe that, and then we will efficiently, essentially, logically wait until that's satisfied. We have a lot of coordination primitives that you can actually stack. There's a little algebra that you can use for the coordination primitive. So you can nest a join under what we call the choice statement. So whichever thing happens first, you take that branch. So you can create your own primitives as well. Now, this is a little visual illustration what the CCR is about. So we're about these things that we call ports. These are very powerful primitive that you pass around, and that's where you interact. Then we're also about these things we call arbiter. These are the coordination primitives, receivers, the joins, the interleaves, which are like reader-writer. So what you do is you attach this constraint on a queue. And you say, do not run my code until the constraint is satisfied. So this process of attaching that on the queue is also happening asynchronously. Imagine a queue already having 1 million messages. If I did it synchronously, that could take a significant amount of time. This is where our dispatcher logic comes in. We have these queues that we pick a message from each, and we execute that task. So someone places a message on that port. Why would they do that? Well, think of ports now as the new API. You don't give classes to anyone. They don't call methods anymore. You just give them a typed port, and they put messages. That isolates the caller from the callee, both in data and execution context. They cannot throw an exception that will affect the caller, the one that posted the message. You're completely isolated. So they post a message. We basically check, we're a very efficient hierarchy, can we consume the message? If we can, we create a task, a little work item, and we set it in one of our dispatcher queues. Now, we find the first available core, and we schedule it for execution. You can have millions of ports and a lot of dispatcher queues. The ports are like 24 bytes. So it's a fairly lightweight thing. And of course, then the overhead of the managed runtime under that. Now, it's still pretty fast, though. So here's some of the coordination primitives. I'm going kind of fast through here. I just want to give you an overview. We have things that you just want to have a piece of code, find me the first available core, execute it. This is how you would use from handler. You pass a piece of an anonymous method, we run it. We also have this iterator handler that I'll show you in a little bit, which is kind of a neat thing that you can use in C#. And then we have the basic primitives, like a receive on a port. Don't wake up this piece of code until I get one message. If you want to persist it, and you have 1,000 cores, and somebody puts 1,000 messages, we will run them concurrently with very, very small overhead. This is where concurrency comes in. You put a little persistent receiver. You have someone post 1 million messages. We will load balance them across your CPUs. And if you have one thread, our overhead is only like 5% over similar code that was written sequentially, which is very good for scaling up and down. We have some other primitives like join, which is basically wait for multiple, but I don't care about the order. You can use join to do protection of resources, and you have no deadlocks. It's a two-phase primitive. You can basically say, if I have this, and I have this, commit. But if I don't, put it back, wait for the next try. So you can do some really interesting things with joins, both for coordinating things and also for protecting resources. OK, finally, we're in the hello world of the CCR. So this is C# 3.0 syntax. I want to make that clear. And we like it. It's very concise. But sometimes it's cryptic. So the first thing you're going to do, and you only do that once in your application, you basically create a dispatcher, which is our mini thread pool. We have no dynamic thread creation. We don't need it. We just use one thread per core, and we can have hundreds of millions of tasks. We don't need any more. Now, the other thing you're going to do is create a little queue that you can interact with our little thread pool. This way, we can do the round robin and the safety. Now, the first thing you're going to do is you're going to create a port, and notice how the port is typed. So if you try to put an int, the compiler is going to give you an error, not a runtime. Now, I'm going to post a string. Fine. Now, after this, I'm going to basically say, OK, let's do something when somebody posts. So I'm going to attach a receiver on the port. You can see with a little extension method, we're taking a receive, and we're attaching it to the port. This is essentially predicating this. This is the piece of code that will run. So up here, I posted this. What happens in some arbitrary thread context in an arbitrary processor, this lambda, this method will execute. This is one time. So if you post another one, it just stays in the port. We also have a version that is persisted. So if you post 10, 10 of them will run. Now here's the iterator version. This is almost 5 years ago when iterators first came out, that the first thing that came to us is like, the only useful thing in my mind was scheduling. So you basically can take a method and you have the C# compiler break it up in little state machines. So the first thing we're going to do is we're going to take an iterative task and I'm going to pass it a method and an argument, which is a port. All right, now here's where it gets interesting. This little yield statement basically says, if something arrives on this port, logically block. Logically. You're going to magically exit this execution context. The scheduler is going to wait until the message arrives. When the message actually arrives, you're going to really wake up here. But no OS thread was blocked. And we're doing asynchronous operations here in a loop. You can do loops now with asynchronous operations. You can have literally hundreds of millions of iterators yielding. It's just 30 bytes waiting on some queue. Then we'll find the first available thread, we will run it. This is now in C#. In the future, you might see it in more languages. But this is just a library. You don't need a new language to do very concise type of asynchrony. Again, as I mentioned, you can do loops, which is kind of cool, I think, when you have asynchronous operations. OK, let's get down to even more concrete things. So you have probably thousands of APM APIs now. So in this example, what we're going to show is we're going to say an asynchronous file read. But I'm going to do it concisely and without having these little delegates wake up and all that. So I'm going to say, instead of a delegate that wakes up when the operation is complete, I instruct the CLR to post on one of the CCR ports. Then I yield. I'm basically logically waiting until the file read is completed. Then I'm going to extract it from the port. It's safe because I don't execute until the yield is satisfied. And then I'm going to do the traditional pattern of end read. It's going to give me the bytes read possibly. And then I'm going to do my I/O, like, do something with that data. But this is an APM pattern. You can use this, the CCR with APM, and just do asynchrony without cascading callbacks. It gets even nicer. We have a stream adapter that instead of you dealing with the APM pattern at all, we basically hide it underneath. And this is a read operation. And the interesting thing here is that we really enter the CCR world. And I think the beauty of the CCR world is that the way you deal with failure is just like any other interaction. It's a message that will be posted on that port. So now I'm yielding to a choice. So either I read the bytes or an exception occurs. When either one is true, I'm going to wake up on the line below. That is really powerful. I have one piece of code, I originate the operation, and I deal with failure on the line below. And here you just do a simple cast. It extracts the typed item from the port. And then we're going to do a chaining here. I have this little example that reads asynchronously from a file and now writes to a file. And I'm doing all this in a loop, which is kind of neat. I don't have to chain callbacks and delegates. So what I'm going to do now is give you a short example of exactly that, of asynchronous file reading. So what I'm going to do is I have 16, a couple of megabyte long files that are images. I'm going to spawn, as fast as I can, 16 iterative tasks that do exactly what you saw. Begin read, update UI. Begin read, update UI. And right now, I'm going to show you something else. I'm going to synchronize with the WPF UI. So I'm actually going to lockstep how I read the file with the updates of the UI. You can do UI with CCR. You can do input control. You can do networking. You can do, storage. So you see how we kind of lockstepped each line? And I'm going to show you, if you missed it, just go through it again. Now what I'm going to do is I'm going to say, let's use one of the higher order CCR primitives. And I don't want to see anything in the UI, but I still want to concurrently process those 16 files. But don't wait for the UI this time. So the speed up you see is also because of caching. NT brought the files up. But it's also 10 to 20 times faster. And what we said was, independently compute, and then when you have all of them, any order, update the UI. Now what I'm going to do is I'm going to do some asynchronous I/O, read the files, but as each file completes, out of order, I'm going to do some really heavy computation and extract edges, gradients from each image. I'm really vision focused these days. That's why you're going to see a lot of vision. So we're reading the files. Now notice, I only have 2 cores, but I use them as much as I can, and I basically computed the gradient out of order across all of them. Okay? So that's our demo. Now, this actual code that did all this, the main part, is this little iterator called read file async. I pass it the file name, and I pass it the index in the WPF app that it needs to update. And just like I showed you before, I do a do, just a little loop, where I begin read, I wait for the result, I update the UI, and here I do a WPF invoke. And I say, okay, update the UI, but I'm going to pass you a port. This port thing is so powerful. When you're done updating the UI in an arbitrary thread context, in the WPF dispatcher context, I'm going to wait for you. Yield return on this done invoke. Wait for the item to be received. This is how I synchronize UI with my I/O. Not that you should do that, but it's a good example that you can have a very heterogeneous type software and use the CCR to do the gluing and the coordination. Okay, so let's get back. What I've described so far is our concurrency runtime. This is the programming model and the engine that is running underneath. But that's not enough. Again, in my opinion, distribution is the mother of it all. Is when you have true loose coupling. That's when you really enable concurrency, you separate concerns. And of course, this means you can have the cloud and a client device. You can have 2 PCs, or your phone and 2 PCs. It doesn't matter. But distribution is really what we wanted to focus on. So we created, again, this different programming model that we thought addressed 3 key things. One thing that people want, of course, when they build complex application is robustness. How do you get robustness? You get it from isolation. We deeply clone your data, and we do it by at compile time analyzing your data structures. When you're in process, it's just like you're across the world, except that we can do 200,000 a second versus 10,000 a second. But to you, you're just as isolated. Remember, everything is using the CCR, so in execution context, you're also isolated. You can use different resources, different cores. Having a uniform concurrency model goes a long way from eliminating errors. Having 10 different ways of expressing concurrency paradigms is a source of errors. The CCR might not be the most concise in all cases. Having a smaller set of primitives you get used to can eliminate a class of deadlocks, live locks, etc. The second thing you want, of course, is composability. Composability falls out of isolation and a good mechanism to find things, to manage things, and to deploy things. The other thing we did is we put publication subscription, which is a very common pattern, and it's now embedded in any little component that you write in DSS. The last thing, which again robotics people told us is very important, is observability. We separate state from behavior. Think of everything as being a living document. If you're stateless, fine, you just do computation. But a lot of services are just a document. Now, what is eventing in that world? It's nothing more than forwarding state changes. We don't have arbitrary events. If somebody sends you an update, you just forward that update. And you can have distributed link queue queries, so you can spread link queue running across the network, and you can gather the results. You can do type filtering, you can do all that. So we have a runtime, but we also have a protocol that we made it available under the open specification promise, so you can implement this in Linux and interoperate with Windows. Essentially, all we did is we took REST, and this is, again, quite a while ago, and we said, What we think it's missing is structured manipulation. It's really great because it has a small set of verbs, and I can consume and produce content very easily. But what if I want to do structured stuff, like notifications when a particular part of my state changes? And that's really all we added, is a small extension on top of REST. Here's what I mean by a living document. The beauty of seeing things as a document is that the UI is always separate from the runtime. You just go to a service, it could be in Australia, you get its current state, and then you do a local transform. You can do that using Windows UI, you can do that using an XSLT in your browser, or you can just get the XML by going on the browser on that URI. Now, what is a service? A service is our little component. It's a C# or VB class. It's annotated with some attributes. And this is really the pieces that it has. It has a URI. It has state. We really want state to be separate and annotated. That's the data structure you use to keep things. And we have service handlers that use the CCR to deal with concurrency, exclusivity, atomicity, teardown. You'll see it's one attribute that you put on a handler, and it can have multiple steps. We will protect you. This is essentially the step that you will go. A lot of them are very similar between service-oriented applications. You have your data structures, you annotate them so they can serialize. In our world, you don't have interfaces. You have messages and ports, because again, we use the CCR. So you define the port and the operations you expect, and then you go ahead and you implement your service, which is just a bunch of handlers listening for messages on a port. Okay, so how does it look? What is state? What is the document? In this particular example, it's just a list of records. This is the state for my service. And in this particular service, I'm going to have a query. This is one of the core operations that protocol supports. And I'm going to say, if you try to talk to me, you can do a query, a get, to get the whole state, or an update. That's our interface, a CCR port. This is what the minimum implementation of that service would look. The runtime will take care of everything. We'll actually hook you up to TCP, to HTTP, to UDP, whatever. We will do the get from HTTP for you. All you need to do is declare some things. Here's really one of the most interesting things. We have this partnering concept. You start an application, and you say, I need something else for me to run, but that could be across the network. So you can define a set of policies that will make the runtime deal with the failure combinations, instantiate that service across the network, if it doesn't exist, hook it up with you, and then start you. You can have these graphs of services literally being composed at runtime across machines. And then when you start, they're available for you. The races have been resolved. And you call base start. We put you in our local service directory. We announce you, essentially. And that's it. We wire you up. All right. Now let's look what a handler would look like. Now remember, what does the service do? It's very simple. It has a URI, and when you want to query something, it will return with some record out of its list of records. So I'm going to show you two handlers here. The first handler is a query. So you will wake up in this piece of code when somebody from the network or locally issues a query. Notice the declaration above. It says concurrent. Literally, somebody puts 3,000 queries, you have 3,000 cores, they will all run concurrent. That's all you have to do. This is not as simple as grabbing a lock around an enumerator. This can have multiple asynchronous steps. We just observe the data dependencies and queue things appropriately. So we don't have the issue, of lock convoys and stuff like that. This is not using locking at all. This is using queuing theory and networking. Now, what happens in an update? In this simple example, I want to do an atomic update. So let's say I have 3,000 updates coming in. I have 5,000 queries. What are we going to do? We're going to quiesce the concurrent operations, let them finish. We're going to let only one update happen, only one, across cores, because that's what you wanted. In your update, you're going to do asynchronous operations. You're protected. You can actually have a state machine that yields to the database, to whatever. You're actually protected. Nobody can preempt you, even between those asynchronous operations. And I jumped too fast. In any case, And that's the example of atomicity. You basically declare as exclusive, and we will take care of this running by itself. Now, let's talk about failure a little bit. It's all nice to generate concurrency, to do event coordination, but failure is really ugly in this world. I have layers of services across machines, across processors. I want to be able to, in a sane way, deal with failure at the level that makes sense. A lot of us write code that does try-catch everywhere. And especially when we do distributed programming, we deal with failure in a pairwise fashion. Otherwise, it will get lost. You will time out. You will leak failure. Here's an example. I'm using our visual programming language to just describe a simple execution graph. So this execution graph has a service that has a notification, and then it basically bifurcates into two pieces that will do things concurrently. So for every notification from this webcam, I'm going to do two separate pieces of computation. What you're going to do in our world is you're going to set a root cause. Think of it as a logical context. Before you initiate any operations, that will silently basically be populated across the system. When failure happens, we, on your behalf, will propagate it all the way up. So if the failure occurs here, one of the side branches, it could actually happen in concurrency. You can have, for one operation, 10 failures, which is kind of a weird concept. But it's useful to know even the number of failures you might get. So graphically, again, what I did, in the root cause, I just pop up a dialog that said, something went wrong. But at the lower levels, I couldn't even deal with failure, so why deal with it? It's just code that doesn't make sense, but I do want to know. Okay, so we're back to demo. One second. I actually want to show you the network interaction diagram. So here's what we're going to do. We have one service, the log syncer, that's going to use one of our infrastructure services to create 1,000 instances of a simple service. So it's going to wake up, send 1,000 creates. It's going to use a CCR primitive, one line, to gather them. They'll execute out of order. We'll gather them all together. The next thing we're going to do, as fast as possible, we're going to issue 1,000 requests to get their state concurrently. And then when we have their state, I'm going to actually start the log syncer service so it's ready to process messages. During all this time, the DSS infrastructure is queuing messages for that service. It's isolating it. Since I just described the code, I actually want to show you how concise this piece of code is. This can be done across 1,000 machines in the cloud. I want to make that clear. It takes one little string to make that happen across 1,000 machines. So we're going to create a port up here that's going to gather the results. As fast as we can, 1,000 of them, we're going to say, do a create operation, pass that common port, and basically tell the constructor service to start them. So I have this port that's bound to an infrastructure service, and I'm posting creates as fast as I can. All right. Now I'm going to use a very interesting CCR primitive, the multiple item receive. And I'm going to say, I'm expecting 1,000 responses. But here where it gets really interesting. Anyone can do essentially a wait for multiple items. What this does is it looks at the type in the port and it notices that it has a fault and it has a success. What we will do is we will do a collection that has all the successes, K successes, another collection that has all the faults, let's say M faults, out of N total. The combination, of course, is combinatorial, but you don't care. You're going to wake up once, and I'm going to give you two bags, all the successes, all the failures. In this case, I only care about the successes, the create responses. Again, what I'm going to do is I'm going to say, okay, I have now the URIs of all those services I created across the cloud or across many machines. In a tight for loop, I'm going to go ahead, create a typed port so I can communicate with those little services, and issue GET requests. So here I am in a loop posting 1,000 or as many successes GET requests. And once again, I'm going to say wait for them all. N failures, K successes. So this total is, I don't know, about 40 lines of code. We create services across. We wait until they're all done. For only those that succeeded, we go ahead and retrieve the state, and we add it on our own state. Right here, I'm going to take all those little values I got and add them on my own state. I'm aggregating. Why would you do that, you might ask? But there are examples that you want to aggregate across the network. You want to do this synchronously. You want to do it at large scales. So by the time I finish this sentence, we've done it. Now, these are powerful little web servers. They use the HTTP kernel driver, and they're tiny, but they can support massive loads. So this is comparable to IIS, except we don't have the management infrastructure. We don't have a lot of the other stuff, but we use the same kernel infrastructure. So we created 1,000 services per second with our own unique URI and retrieved their state. Since I've done that, why don't I bring up my browser? Because remember I told you observable? I'm going to interact with the node right now. We're by default secure. Everything I told you, we use the Windows networking infrastructure. Unless you're authenticated, you can't access any of that. But we separate concerns. We don't want the obscurity of your code to make you secure. We just want a security system. Other than that, everything's out in the open. The state is there. You can bring up your browser, monitor every single state. This is kind of our home page. All it tells you is that you have really two services. I'm hiding the system services. If I don't hide them, you see the other system services already started. And here we have 1,000 instances of this little log source. And then I have a single instance of the log syncer, the thing that did the aggregation. OK, let's see how it looks. I don't really have a fancy UI for this service. So I'm just going to get true REST. I'm going to get its representation. What is it? It's a list of GUIDs. That's all I did. Create 1,000 services. Each one had a GUID. And then I put it all in one list. At the most basic level, that's a service. Now let's go back. Clearly, that's not a very user-friendly thing, especially when it has GUIDs. So we have other services we've written. Underneath, they're the same. But look, someone in our team took about 10 minutes to write an XSLT. It transforms the XML into HTML. So this looks a little bit better. This is our service directory. This is where you see all the services that are started in the system. Again, you want to get the raw view? Fine. We basically give you the records underneath. This is the state of each service that has started in this node. Here's how our CCR bubbles up. Again, everything is observable. So you can issue a message through the browser, and you can see our dispatcher. This is the mini thread pool. We use one thread per core, but a dispatcher queue per service. So we can round robin. Look at all of them. Now let's stop a little bit and say, for this log source instance, this is a serialization of the data for the dispatcher queue. It's not using the thread pool. It has no messages right now pending. And look at the policy. It says unconstrained. If you had done throttling, it would say, throttle execution based on queue depth. Throttle execution based on task rates. This is where this will up. Again, I just bring up my web browser. I experiment with my system. People are running 50,000 servers with this runtime right now. When you're talking between machines, we don't do HTML. We don't do XML. We just do binary, and we do sane stuff. But it's still nice, because humans are still in the loop, to be able to interact with the system. But this is not something you do on the side. This is what we are. We are a document. Everything else is on the side. Okay, probably talked too much about that. Okay. Now, I told you earlier that we have this visual language. So visual languages have a lot of issues, but they are good for one thing, in my opinion. It's much easier to discover what you have. I'll show you in a little bit. We'll go on your hard drive. We'll find all the services we've written. They'll show up on the left. You drag and drop. You at least know what you have. So it's a very nice way to explore what you have. The second thing about them is they visualize our very pure model underneath. And when I say purity, I don't mean in the sense it's the only right thing to do. I just mean that we have a very small set of primitives. So we have notifications, we have request responses. It's very easy to see what each service does in the visual language. The next thing you do is you wire them up, just like a million other visual things. but they're pure data flow, and we know the concurrency implications of your actions. If we see an update go in the visual language through a complex execution graph, we will take the entire execution graph and make it non-preemptible. I don't know if I can express how powerful that is. Without you saying, protect this state machine from being preempted, because we notice that you're doing a state side-effecting operation, we will protect it. Again, no locking, of course. It's just a data dependency graph that we will build. So here's a visual of the visual language. On the left is the available DSS services. They're assemblies. They're just .NET assemblies. We go on the disk, we grovel through them, and we find all kinds of interesting things about them. They're self-documenting. They have a URI that points to their MSDN, documentation page. This is an example of a service instance. I will drag and drop, bring it here. And here's an example of wiring. I basically take the type, let's say an update notification, and I wire it to this particular service. And out here, the response will come out. Now, I can take this whole graph and make it one activity. So I can collapse, nest, compose. The second part, some people just really have an allergic reaction to visual programming. So I'm like, fine, don't use visual programming. But would you like to deploy your application? We have this little tool, essentially part of the visual programming language, but it's standalone executable, that based on the metadata that we found for your service, we know what partnerships it needs. So I can compose an application that has 5 pieces, and I only drop in the right piece because it's type safe in a meta sense. It knows it needs a webcam. It doesn't take, a SQL front end. So it's a nice way visually to just create a little manifest and then deploy it. It gets a little bit better. Again, you would think this is way overkill for robotics, but a lot of people are doing distributed robots now. One of the basic images I had in the front, it's for the French military running our stuff. It's using 3 laptops and Wi-Fi, sending thousands of messages per second across them. And it's running across 3 PCs. These guys want to have one place that they specify the behavior of the program, and then you affinitize them. You say, I want this one to run on that computational domain. I want this one to run in that computational domain. You can understand this is much more powerful than just robots, which is why we're making this available for external use. Okay, now I'm going to give you an example of building such an application that has multiple pieces, and it does something interesting and really relies on the CCR. I have to tell you, I'm in robotics because we need no excuses for concurrency. If you had like 1 billion cores today, we will use them. It's just such a hard problem that we would use any processing power you have. So any demo I'm showing you now, we are using this to solve some really hard robotic applications, robotic problems. So this is my feature extractor, but I'm going to use the visual tool. This is our manifest editor. It dynamically enumerated all the services that I have on my hard drive in a sandbox. I'm looking for a particular service, which is a validation service for image processing. I'm going to drop it in. Ugh. If I could use the mouse. There we go. Now, notice that we already analyzed this service, and it told us, because declaratively, remember I showed you had this partner attribute? That's what we saw here, this partner attribute. It says I need a webcam. Fine. Here's the webcams we have. We actually have this notion of a generic contract and can have multiple implementations. So I'm going to choose the USB webcam and drop it in. It also needs a feature extractor. This is a way that you're taking an image and you extract features so you can do comparison. So here's 3 different algorithms that we've cooked up or using from MSR that do feature extraction. The last thing it needs is an image database, something that can basically do kind of a relational lookup, features from different scenes, and tell you what you're looking at now matches best that scene. The motivation for all this? Completely autonomous navigation that needs nothing more than one camera. So it's a very powerful thing if you can pull it off. We're not done yet. Okay. The other thing I can do from this editor is initialize it. Initialize the state. Remember we're a document, right? I can bring that document from a URI in Australia, or it can be a file on the disk. I don't care. I can suck it up when I start. I'm initialized. So here I'm going to import a particular document, because what I wanted to do is basically tell you where to look for the images. And it's this directory. But this is a C# data structure. It's serialized on disk. And I'm saying when you start, use this. Let's overwrite this guy. Yes. Now all we're doing essentially is starting a DSS node that you've seen before. But we're also running a little WPF service that is really the orchestrator. So it issues 30 times a second. It issues a request to the webcam. This can be across the network. As far as it's concerned, it's using DSS. It can be across the network. It passes it through a feature extractor, yields. I'm using iterators everywhere to make the code really concise. And then it will register that in the database service. So here's what I'm going to do. I'm going to say capture frame. So right now it's saying, OK, this is what you're looking at. Don't get scared. No, you're looking at George now. This is the best match. Notice how invariant it is. This is not a joke. I mean, I'm rotating the thing. It's finding the features. George. George. You. Now, the other cool piece is we really rely on the CCR for everything when it comes to coordination. So right now, we're load balancing across cores, but we're not pegging them. That's usually a good thing. Now, I'm going to start adding images like crazy. Notice that, again, across processors, we're load balancing fairly equally. And we're doing asynchronous I/O and all that good stuff. Okay. All right. Oh, the one thing I wanted to show you earlier, but I didn't have the time, and I probably won't have the time now, is by the time I finished this demo, there was probably 40 or 50,000 concurrent tasks that had executed at the task granularity. And that's it. So we're here with a new product that essentially a product that's already been available, that it's been made now available on its own. You can enterprise customers like Siemens and Tyco and Live and some others that we can't talk about yet are using it. It's lightweight. It's truly lightweight in working set, in number of lines of code, and all that. And you can use it today. So the website is going to go live tomorrow. It's not live yet, but you can go there to download it, to get the tutorials, to get the case studies. There's some videos. And we have a community forum and some more channel line videos. Thank you. Thanks. So if you have any questions, you can come to the microphone, or you can talk to me at the booth, or I don't know.
I'm just curious how this relates to the other parallel and concurrent initiatives. So the managed code task parallel library, and Rick Molloy yesterday was talking about the C++ concurrent runtime.
So the question was, how does this relate to the other efforts that we have? And this effort, has its own programming model. Right now, it's not directly related, but we're working with the team to, first of all, use their scheduler underneath, so we don't duplicate the underlying runtime. But our primitives will stay pretty much as they are now. So you'll get this other programming model using the common native runtime. But it's a different programming model, so we're giving you a choice versus TPL or features or whatever. And you can use this for everything, or you can mix and match.
That's great to share the runtime.
Yeah.
Kind of on that same note, I was wondering if this is going to make it into the BCL at any point.
Yeah, and that's the hope. I mean, it's not going to be the short term, but in a couple of years, the hope is that it will make it in the core .NET.
Will you be able to throttle based on database performance or other counters?
You can do that by creating your own counter. We don't, of course, do that on our own, but you can create a little predicate. I didn't show that, but you can have receivers and predicates on receivers, where you can read another counter and say, I'm not ready to queue this up. So you can do this now. We actually have people that do interception of messages lawfully, and they use database lookup inline to do this type of throttling.
So if the task that you're looking to run is non-managed code and it might be something that's pretty CPU intensive, will the one thread per core stop, say, hey, this core is busy and stop scheduling, or will it continue to schedule other things? Like if the stuff that's on each core that's non-managed might be I/O bound or something.
So this is actually a very good question, which is if you have something that's non-preemptible and you're executing in CCR, it will take up that core and we cannot preempt it.
Okay.
However, from the very beginning, we knew that's the reality. Some people might use synchronous code, might use computational code, intensive code. This is why we have multiple dispatchers. Today in DSS, with one annotation, you say sharing false. That component will get its own thread. It will be isolated from the other nicely playing components, and it can take its time. But we don't have one thread pool. We have a composition of thread pools, either for COM interop or for this type of interop and all that.
Microsoft doesn't have an RTOS offering. Do you guys foresee that this will be put into an embedded platform?
So you can use this today on the compact framework, and we actually have people that are using it on the micro framework. But the rest of the infrastructure, again, doesn't give you the right levels of jitter and determinism.
Right.
We are looking at various ways that this could become the norm for deterministic interaction, but nothing concrete yet.
So nothing yet.
Yeah. But you can use it in the compact framework and the micro framework and embedded devices. Yeah.
Thank you.
Can this be natively ported to C++ at some point, or is it only .NET?
So the question is, can we talk to native components? We talk to native components all the time, but we don't do anything about that. We just use the normal CLR mechanisms. What we usually do is we have a managed C++ class that we talk to it just like it's any other managed component, and that talks to a C component. That's very clean. We have a lot of native interop. I mean, we're dealing with all kinds of weird devices that only have native C code. And we write this little C++ wrapper, and then it looks like a CCR component. So it's quite easy to do.
But you won't be building a C++ library of this runtime?
No, this runtime is only managed. It doesn't have any native components whatsoever. Okay. Thank you.